Our last target is analyzing the scientific concepts of work and power. And in order to do that, we first need to answer the question, what is work? Well, work is the scientific concept of energy being transferred through motion. So when energy transforms, there's always going to be motion involved, whether that's particle motion or like macro motion. So when that happens, that means we're going to be doing work on an object. And in order to do work on an object, there's two qualifications. First, the object has to move. And second, the force applied to the object to make it move has to be in the same direction as the motion of the object. Or in more sciencey terms, force and motion must be parallel. Down here we have 3 examples, and we're going to discuss each one of these to see if we're doing work on that object. The first is pushing on a wall. So here's the wall, here's you, and here's you pushing on the wall. Now, no matter how hard you're pushing on the wall, there's going to be no motion, even though you're applying a force on the wall. So if we look at our 2 qualifications, first, if the object has to move in order to do work, and the wall isn't going to move, that means that no work is done on the wall because it's not moving. Our second example is if you carry a book across the room. So here's you carrying a book across the room. In this case, the book is moving. The book is moving to the right because that's the direction that you're walking. However, the force you're applying to the book is going up. So when you're carrying something, you're applying an upward force to keep it off the ground. If we look at our 2 qualifications, the book fits the first one. It's moving. However, the force being applied is going up while the motion is going to the right. So they're not going in the same direction. So that means that no work is being done on the book because force and motion are perpendicular. Which means that they're not going in the same direction. Our third example is picking a book up off the floor. So here's you picking a book off the floor. In this case, if you're picking a book off the floor, the motion of the book would be going upwards. And so is the force, because you're still applying an upward force to the book if you're picking it up. If we look at our 2 qualifications, the book is moving, so it fits the first qualification, and the force applied is in the same direction. So in this last example, work is done on the book. Because force and motion are parallel. Which means that they're going in the same direction. In order to calculate work, we're only going to use this formula. Work is symbolized by a W. So W is the symbol for work. Force is an F, and we're going to times it by distance, which is D. Now, the unit for force is the Newton, while the unit for distance is the meter. And in Newton meter, we learned at the beginning of the unit is equal to a joule. So joule is the unit for work. In our first guided problem, it says how much work, so we're looking for work, is done when a 500 Newton force, so 500 newtons is our force, is used to move an object 5 meters. Meters is our unit of distance. So we're going to need to show our work, no pun intended. So work is equal to force times distance. So 500 newtons times 5 meters is equal to 2,500, and our unit for work is the joule. Our second problem asks how much work, so we're looking for work again, is done when a 350 Newton force, okay, so that's a force, moves an object 2 meters, and meters is our unit of distance. Again, we're going to do all of the steps. So work is equal to force times distance, where we have a 350 Newton force times the distance of 2 meters, means that we did 700 joules of work. Naturally, if you're doing work on an object and you're moving it across any distance, whether that's a millimeter or a mile, it's going to take some period of time, whether that's a millisecond or less or hours. And that brings us to power. Power is the rate at which energy is transferred through motion. Or, in more teenager-friendly terms, how much time it takes to do work. So power is produced or used whenever energy is transferred. While we use joule to represent potential and kinetic energy and work, power has 3 units, but luckily we're only going to use this one. However, we're going to make you aware of all 3. Power is normally expressed in a watt, which its symbol is the W. So 1 watt is equal to 1 joule per second. Another unit that power is expressed in is kilowatt, where 1 kilowatt is equal to 1,000 watts. Sometimes light bulbs are given this unit. But you might have heard of kilowatt hours, or kWh. This is used on energy bills. So if you're bad at turning off lights like I am, when I was growing up, my parents would always threaten to have me pay the energy bill. And when I learned what a kilowatt hour was, it made a lot more sense. The last unit is horsepower, and this is usually used in car engines. And 1 horsepower is equal to 746 watts, which is pretty specific, but this is our conversion factor from horsepower to our normal unit of watts. In order to calculate power, we have this one equation where power is equal to work over time. So power is represented by a capital P, and it's equal to work over time, where this W represents work. So remembering our unit for work from the front side of our note sheet, that's the joule. And it's divided by time, which is our base unit of seconds. And 1 joule per second is equal to a watt. This is semi-problematic, considering that work is represented by a W, and so is watt. Now, some students are usually troubled by the fact that W is in 2 places in the formula, meaning 2 different things. When we do these in-class practice problems, I'll give you a strategy to help you alleviate that overwhelming feeling. Our first guided problem says you can pull 140 newtons, okay, so newtons is a force, of weight a distance of 1 meter, okay, meter is a distance, using a rowing machine. A asks, how much work did you do? Well, work is equal to force times distance, and that's from the front side of our note sheet. So we have 140 newtons of force times 1 meter of distance, which is going to be equal to 140 joules of work. B asks, how much power did you have if you pulled the weight toward you in 2 seconds? This is where that strategy is going to come into play. So power is equal to work over time. So we did 140 joules of work, and we did it in 2 seconds, which means we did 70, so that's 140 divided by 2 watts of power. You may not have noticed, but what I did was I wrote out the word work and I wrote out the word watts. That usually helps students in terms of differentiating between the two W's and ensuring that they tell the teacher that they understand what's going on. C asks, would your power increase or decrease if we doubled the amount of time it took to pull the weights towards yourself? So originally, we had 140 joules over 2 seconds. If we double the time, that means we're going to times it by 2. So we're still going to do 140 joules of work, but in this case, we do it in 4 seconds. If we increase the time, we are going to decrease the power because time and power have an indirect relationship. If you're more math-minded, when we double the time, time is in the denominator. So if we increase the lower number, that means our answer is going to be smaller. So again, if we increase the time, we're going to decrease our answer, which in this case is power. Question 2 says that your strong friend can pull 280 newtons of weights. All right, so we have 280 newtons, which is a force, a distance of 1 meter, which is a distance, on a rowing machine in 2 seconds. Question A asks, how much power do I have? Okay, so power is equal to work over time. But I didn't give you anything in joules, which means we're going to have to split work into its components, which is force times distance. And we're going to bring over the time from the last part of the problem. Our force is 280 newtons times 1 meter. And our time was 2 seconds. 280 newtons times 1 meter is going to be 280 joules. Then we bring over 2 seconds. 280 divided by 2 is 140 watts. If we look at our problem, we see that when we pulled the weight, we had 70 watts of power, but our friend has 140 watts. So let's talk about why they have more power than we do. If we look at the problems themselves, we see that we pulled 140 newtons and they pulled 280 newtons, the same distance in the same amount of time. So the only difference between our friend and us is that they pulled more weight. And we learned in our third unit that weight is a force. So if they pulled more weight, that means they did more work. Which means they had more power. So if weight increases, which means force increases, that means work increases and power increases. This means that force, work, and power have a direct relationship.